Algebra 2 honor students, there's going to be unit 8, sorry, day 3, which is going to be some tools for digging for the roots. So we are at a point right now where in order to find all the roots, I've given you some big hints, right? I've either told you a root, I said, hey, test this as a factor, but it's going to get to a point where I'm not going to give you those hints. I'm not going to say, test 4, test negative a third, like we have in the past few lessons. We're going to have to develop a way to determine what roots even make sense to test. And if I have a really long list of roots to test, what are some other options that I have available to me that would make it such that I can narrow down that list? So today we're going to talk about a lot of different tools for digging for our roots. What I want you to get started with is, given this polynomial, 2x cubed minus 3x squared minus 11x plus 6, I want you to test both positive and negative 6 with synthetic division. Okay, so test 6 with synthetic division, then separately test negative 6 with synthetic division. And then once you're done, we're going to analyze the results. So hit pause real quick because I'm about to reveal the correct answers by testing each of these roots. And the first thing I'll show you is I tested negative 6. And when I tested negative 6, brought down the 2, you see that things go off the rails pretty quickly in terms of these values are getting bigger and bigger and bigger, and eventually you get a remainder of negative 468. So when I go to graph this function, I know that negative 6 comma negative 468 is a point on the graph. Similarly, when you test positive 6, these values start to grow pretty quickly, and you get that the remainder there is 264. But even though these are not roots, there are some good conclusions we can draw about testing negative 6 and then testing positive 6. So the first conclusion I'd like you to list is for x equals negative 6. X equals negative 6 is called a lower bound for the function p of x, which means that there are no roots lower than x equals negative 6. So if I were trying to test and find the roots of this polynomial, I'm not testing negative 7, negative 8, negative a million, negative 9.2, decimals, fractions, anything less than negative 6. It is guaranteed that it will not work when you determine that something's a lower bound. Well, how do I know that this is a lower bound? Just by doing that synthetic division. In general, if you test a negative number and the signs alternate, they go from positive to negative, from positive to negative. Look at the signs in our synthetic division. Positive, negative, positive, negative. They alternate down the line, however many signs you have. That is indicative of a lower bound. So don't test negative 7 or any other integer, fraction, rational value less than negative 6. So if negative 6 is a lower bound, you're probably going to be a good guesser about what x equals positive 6 is. And you've guessed it, that x equals 6 is called an upper bound. It's an upper bound for the polynomial p of x, which means there are no roots that are higher than x equals 6. How do I know that we have an upper bound? Just by looking at our synthetic division. We have 2, 9, 43, 264. Well, it's a little bit easier than even lower bounds. The whole row is positive. In general, if you test a positive number and the whole row goes plus, 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 the signs are all positive, it's an upper bound. So that is helpful in that I wouldn't test anything larger than 6. If I had a list of roots and there was something in my list that was bigger than 6, I just wouldn't test it. I know it's not going to work because of this rule. So there are some other tests that we're going to learn today, but lower bounds and upper bounds, when we notice them, can be very helpful. The problem is sometimes we forget to look for them. So when we do an example at the end of the lesson today, we'll try and point it out and see why it can be so helpful to identify lower bounds and also upper bounds. Okay. Another big thing we're going to talk about today is, how do we even know what we should be testing? I mean, I said test negative 6 and 6, but I can't just forever tell you what to test. So how do we know what we should be testing? We're going to talk about something called the rational root theorem, another tool for digging for the roots. Okay. What does the rational root theorem state? It says that the possible rational roots of p of x are the factors of the last coefficient divided by the factors of the first coefficient of your polynomial. And I'll show you what this looks like for the example that we looked at up above. So again, the possible rational roots that the polynomial could have are all the factors of the last coefficient divided by all the factors of the first coefficient. So let's take a look at what that looks like for the function p of x that we started today with. So 2x cubed minus 3x squared minus 11x plus 6. I'm going to take the factors of 6, and then I'm going to divide them by the factors of 2, and that's going to give me my list of roots that I would potentially test using synthetic division. So here are the factors of 6, plus or minus anything 1, 2, 3, and 6. Could be plus or minus because, of course, -1 times -6 could give you positive 6 there. And then the factors of 2 are plus or minus 1 and 2. So based on those possible factors, I'm going to take everything on the top, divide it by 1. So that's going to be 1, 2, 3, 6. Then take everything on the top, divide it by 2, and you should get a few new roots to result from there. Here is the list of possible rational roots. Like I said, if I take everything and divide it by 1, I get 1, 2, 3, 6. If I take everything and divide by 2, I get 1/2. There it is. 2 over 2 is 1, which is already in the list. 3 halves, and 6 over 2 is 3, but that's a repeat from the list. So if it looks like I have a list of 6 roots, it's actually a list of 12 roots because it's plus or minus any of those possibilities. It's going to take me a long time to find them if I have to test all 12, but we have other tools that we can use to find the roots quickly, such as upper bounds and lower bounds now. We also have that root location theorem from yesterday, which says if you see a sign change between the y values when you're doing synthetic division, those remainders, then maybe there's a root in between. So rational root theorem, we're going to actually take this list. I'm going to pick a specific number from the list and find all the rest of the roots for this particular cubic polynomial. The one that is my favorite in that list, just because I'm a really good guesser, is let's test x equals 3. So we're going to test x equals 3 and then find all of the other roots. Okay. So when I do that, we're going to put 3 in our box over here, and the coefficients from the polynomial are 2, -3, -11, and 6. So bring down the 2. 2 times 3 is 6, plus -3 is 3. 3 times 3 is 9, plus -11 is -2. -2 times 3 is -6, plus 6 is 0. So we found that 3 is in fact a root. I was a very good guesser. Take the remaining coefficients, make your quadratic 2x squared plus 3x minus 2 equals 0. It's not ever guaranteed that this is factorable. So if you don't know how to factor it, or if it's not factorable, use quadratic formula or use complete the square. But this one I'll tell you does happen to be factorable, I believe. So we've got 2x and x here. If you put plus 2 with the x and minus 1 with the 2x, the outside is 4x, the inside is -1x for a total of 3x in the middle. So the other two roots would be x equals 1/2 if I set that to 0, and x equals -2. So my roots in the end are -2, 1/2, and 3, which I tested up here in synthetic division. Now, the thing that's great about that list of roots in the end is because they are all rational roots. And by the way, this list is only a possible rational root list. We could have irrational roots that, of course, wouldn't pop up here. The other roots that I got as answers, -2 and 1/2, those appear on my list. -2 would be there, and so would 1/2. If I factored and got like 4 and 5 as my other roots, I'd be in big trouble because they're not even in this list. So I would have had to have made a mistake somewhere. But because of the result in the end with all those rational roots, you should be able to go back and double check your rational root list to see if you're on the right track. All right, let's talk about our last tool. Last tool for now is going to be something called Descartes' rule of signs. And Descartes' rule of signs tells us about the nature of the roots. So Descartes is a famous mathematician. And his rule of signs helps us determine how many possible positive roots, negative roots, and complex roots there would be in a polynomial. Okay, so there's two things we're going to look at. One thing we're going to look at is the sign changes in p of x. And if you look at the sign changes in the original polynomial p of x, this is the max number of positive roots that the polynomial could have. To figure out the max number of negative roots that the polynomial would have, you're going to look at the sign changes in p of negative x. So like I said, that's max number of negative roots. And what Descartes determined is that because these are a max number of positive and a max number of negative, it may not actually be equal to the number of sign changes in either p of x or p of negative x. It may be less than that, or less than that by an even integer. And we'll talk about why it has to be less than that by an even integer when we go to set up our cases here to determine the nature of the roots. So let's see. Our function that we've been really studying pretty hard today so far is p of x equals 2x cubed minus 3x squared minus 11x plus 6. So the first part will be pretty easy for us. We're going to look at the sign changes in p of x. So the signs that I'm talking about are the signs of the coefficients. I'm looking at the first coefficient is a positive 2, then it's a negative x squared, a negative x term, and a positive 6 at the end. How many times do we change sign from one term to the next? Well, right away I switch from positive to negative. Then I go negative to negative. That's not a change, but negative to positive. There are 2 sign changes in p of x. What does that 2 represent? It's the maximum number of positive roots that this polynomial can have. How do we do then p of negative x? Well, to do p of negative x, I'm going to switch colors here. What we have to think about is if I plug in negative x for all these x's, just these 3, right? You can't plug in at the end. What would change the signs? Would they all change? Would just some of them change? Well, raising a negative to an odd exponent would create a negative coefficient out front. But squaring a negative or raising it to an even exponent wouldn't change the sign out front, because squaring a negative actually just makes it positive again, so it's not going to affect that sign. So if it's an odd exponent, change it. So this is going to be negative, but if it's an even, keep it negative, or keep it whatever the sign is. X to the first is odd, so we got to change it to positive. The constant said that since there's nothing I'm plugging in at the end, I can't plug in a negative x here. The constant always keeps its sign. Notice how there's only one sign change in the middle. You go negative, negative, but negative to positive is a change, but then it stays positive, positive. So what you're going to do off to the side is you're going to make a chart. And the chart's going to have 3 columns. P, N, and C. I think it's obvious what P stands for and N stands for. P is positive and N is negative. But C stands for complex roots. Remember, complex is something of the form A plus BI form, anything with imaginary roots. Well, if you have 2 positive and 1 negative, I know that we have no complex roots because it's a cubic polynomial. Each of these rows has to add up to 3. You can only have a max of 3 roots if it's a cubic. But since we said it could be less than that by an even integer, you have to ask yourself, can you subtract 2 from either of these columns? The answer is yes. You can subtract 2 from the positives. That would be a 0 then. Where does that 2 that I subtracted away go? It goes over to the complex column. So when you consider the other possible scenarios by reducing it by an even integer, you have to take them away from an individual column first and foremost. So you can't take one from here and one from here. But as soon as I subtract 2 away, they kind of slide over as possible complex roots. And that's the only 2 cases here. In the end, the roots for this polynomial should be 2 positive and 1 negative, or it should be 1 negative and 2 complex. It's one of those 2 scenarios. By the way, you already know how it turned out, right? It was 2 positive and 1 negative. So we can always use this as a test, and we always will use it as a test to be able to determine the roots at the end of the day. Okay, let's try another one just to make sure we have the right idea. We'll do a 4th degree polynomial. So if we have 3x to the 4th plus 2x cubed minus x squared minus 8x, and then plus 1. Here's my 4th degree polynomial. We're going to look at the sign changes first of all for p of x. So just go across the way and copy down the signs if they're positive or negative. So it goes plus, plus, minus, minus, plus. So we've got a sign change here and a sign change there for 2 sign changes in p of x. That's the maximum number of positive roots. For p of negative x, we discussed that anything with an odd exponent will change. So x to the fourth stays positive, x cubed changes, x squared stays negative, x to the first will change to positive, constant stays positive. How many sign changes do we have here? One right at the beginning and one kind of in the middle-ish, negative over to positive. There are two sign changes in p of negative x. So when you go to make your chart, notice I extended the columns a little bit further this time. We're going to need it. The first row of your chart should say 2, 2, 0. Because at a max, you'll have 2 positive. At a max, you'll have 2 negative. Why do I know 0 complex? Every row in this chart has to add up to 4 because it's a 4th degree polynomial. So if I follow some of the same rules that I used up here, reducing a column by an even integer, we could also have 0, 2, 2 for the roots. If I decrease the positives by 2, maybe those will be 2 complex roots. I could have left the positives at 2 and decreased just the negatives, made that a 0, and considered that those might be our complex roots. So another possible way for the roots to turn out would be 2, 0, 2. And finally, the last case here would actually be 0, 0, 4. You can reduce both of them by 2 at once, and in the end, have 4 complex roots. So we're going to do more with Descartes' rule of signs. It takes a little while to get used to it, but I promise we'll do so much practice with it in this unit that you'll think, how did I ever not know Descartes' rule of signs? Last thing we're going to do together is put all of those pieces together to find all of the roots of a polynomial. We're going to use Descartes' rule of signs. We're going to use rational root theorem. We've learned a lot of tools in today's lesson. I want to start putting all these ideas together into one problem. So we're going to solve p of x equals 3x cubed plus 8x squared minus x minus 10. Okay. So you don't necessarily have to go in this order, but I do like usually starting with Descartes' rule of signs, which is looking at the sign changes like we just saw in p of x and p of negative x. P of x goes plus, plus, minus, minus. Just looking at those signs, there's one sign change there. P of negative x, if I just change the odd exponent signs, that's going to become negative, positive. This would become positive here. Constant stays negative. So you've got 2 sign changes there. Here's what the chart should look like. First row, 1, 2, 0. Max of 1 positive, max of 2 negative. There would be no complex roots. The next row would say 1, 0, 2. I can decrease the negative column by 2 and consider possible complex roots from that. And with a cubic, the nice thing is that there will only ever be 2 cases. So we can have 1, 2, 0 or 1, 0, 2. Those are the only possibilities we have. All right, moving on. Rational root theorem. Do you remember what that was from earlier? Well, I hope so. Rational root theorem says take the factors of the last term, divide by the factors of the first coefficient. Just to kind of name them, I usually will denote them as P and Q. So if you see that in my notes ever, formal definitions of rational root theorem typically will have P's and Q's there. Don't ask why, because I don't know the answer. All right, so if I take a look at the factors of P, we get plus or minus the factors of 10, which would be 1, 2, 5, and 10. And then Q would be the denominator of the factors of 3, plus or minus 1 and 3. Oops, that was a weird 3. So I got to take everything on top and I have to divide it by 1 first. So that's going to be 1, 2, 5, 10. Then I have to take everything on the top and divide it by that funny looking 3 to get 1/3, 2/3, 5/3, 10/3. Uh-oh, got to really squeeze this in here. 1/3, 2/3, 5/3, 10/3. You can see our rational root list is pretty long. So how am I going to eventually reduce this list? Well, maybe by finding sign changes, upper bounds, lower bounds. We have a lot of different tools to use. I'm moving on to SD. I'm moving on to synthetic division. Here we go. Just because 2 is my favorite number, I'm going to test 2 first. I really like 2. So I got 3, 8, -1, and -10 are the coefficients. I'm going to move a little bit fast through this synthetic division. Ready? Bring down the 3. 3 times 2 is 6, plus 8 is 14, times 2 is 28. Plus -1 is 27, times 2 is 54, plus -10 is 44. Did you think I chose 2 because it was a root? No, it's not a root. Darn. Okay, so it's not a root. However, what do we know about x equals 2? X equals 2 is an upper bound. How do I know x equals 2 is an upper bound? I tested a positive and it goes plus, 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 plus. All the signs are positive, which means there's nothing in this list higher than 2 that could be a root. So it wouldn't make sense to go to 5 next if 5 is your favorite number. 10 doesn't make sense. 10 thirds is also bigger than 2, so I wouldn't test that if you really love 10 thirds. All right, so maybe I need to slow down a little bit. Let me go back and test 1. Maybe 1's my favorite number. 3, 8, -1, -10. Bring down the 3. 3 times 1 is 3, plus 8 is 11. 11 times 1 is 11, plus -1 is 10, times 1 is 10, plus -10 is 0. Got it. Okay, so I did choose 2 on purpose, guys, just to show you what an upper bound would look like and to show you that it wouldn't make sense to choose anything in the list higher than 2 to test next. Okay, so finally, take your quadratic, 3x squared plus 11x plus 10, and solve it. You got to play around with the factors a little bit here to figure out if you're going to use guess and check type factoring, but 3x and x multiplied to 3x squared. 10 could be 1 and 10 or 2 and 5, some combination there. If you put plus 2 here and plus 5 there, that's not correct. So we got to switch it. Oops, I got ahead of myself. If I put plus 5 here and plus 2 there, that didn't work, right? Because it was 17 or 15x plus 2x, which is 17x. Here it's 6x plus 5x, which is the 11x. So I did that on purpose to show you that it's not so scary when you make a wrong guess at factoring. Of course I did. You get x equals -5 thirds from this factor, x equals -2 from that factor for a total list of roots here. What are they? -2, -5 thirds, and don't forget, when we did synthetic division, we found that 1 was a root, okay? This is where we're headed in the unit, putting all of these pieces together. Descartes' rule of signs, rational root theorem, both talked about today. Pretty heavy concepts, a lot more practice to come. Synthetic division, we've been doing it since the beginning. We should be pretty good at it by now. Finding all the roots, making complete sketches, we've got this. You're going to love this unit, by the way. It's really a crowd favorite usually. If you have any questions about what we did today, we'll recap more tomorrow. Have a great rest of your day.